Okay, I'm actually like really excited about today because what we're going to talk about is something called the arc length parameterization and curvature. And I know I talked about this previously, but there's this whole um, field of study called differential geometry, and it was sort of like the thing that like really, well, it was like one of two things that really got me interested in higher math. Set theory and differential geometry, I think, are some of the most like interesting shit ever. So we're gonna be like learning more about this today. So I'm gonna go into writing mode. Okay, where did it go? Oh my god. Come on. Where are you, window? Okay, there we go. So we're gonna talk about arc length, curvature, and a bunch of other cool stuff. This is exciting stuff, dude. So exciting. It actually legit is. Or at least I think so. Okay. So, where's my pen? Let's do this. Okay, so do you guys remember the arc length formula for parametrized curves for a parametric equation? Okay, so like if you have like a plane curve where you have like some function which gives you an x coordinate and you have like a function which gives you a y coordinate, you can calculate the arc length from a. So let's just like draw the picture for this. You have. There's your axis. So you have some sort of curve that looks like this. Okay, so if you look at a point on this curve, let's just do it in green. If you look at a point on this curve, you have some x value, comma, some y value. Alright, so right there could be like x of t naught. So like, let's just say right here is, actually, yeah. This is going to be x of like t naught, y of t naught, and then over here you could have like x of t1, comma, y of t1, right? So you move along that curve by you're parameterized by a t value. Okay, so you can talk about the arc length from t naught to t1. In other words, this distance right here, right? Because you're parameterized by a t value, not an x value. Okay, so how would you find this? It's the square root of x prime t quantity squared plus y prime t quantity squared dt. Okay, we talked about this like earlier this semester, right? I just want to like see if people remember this. Do we remember talking about this earlier this semester? Okay, cool. So, interesting thing, like this formula looks really annoying and complicated, and one of the things that one of the reasons behind why they invented vector calculus was to simplify a lot of these formulas. So like what you can notice is that if you have a pair of parametric equations, you can actually use this to define a vector function. So the vector valued function r of t in component form can be x of t, comma, y of t. Okay, so then you can have a vector. Here, let's zoom in so you can see that a little better. Actually, let's just make that bigger, I guess. Okay, I'm going to redraw that, but I'll make it bigger. Here, we'll just draw it over here. Okay, we're going to move this. Okay, so I'm going to redraw with more space. Okay, so you have the vector valued function r with these x and y components from the parametric equations. Okay, and let's insert an x and y axis. Okay, and then you've got your function. Okay, so this point right here, that's going to be x of t naught comma y of t naught. And then this point over here is going to be x of t1 comma y of t1. Okay, and then the arc length between them is that little squiggly distance right here, right? Which we're calling s up above. Okay, now you can think of this as a vector valued function. You have a vector which goes to that point. Okay, so you could think of this as the vector r of t naught. Okay. And then you can have another vector that would be made by this vector valued function. It would go over to here. And then that vector is r of t1. Okay. And you can find the distance between these two vectors like with that same arc length. But so we're gonna recast this arc length formula in terms of these vectors. Okay, so I want to remind you, if you have some vector v with components a and b, then what is the magnitude of this vector equal to? Well, it's not x squared plus y squared. Well, I mean it is, but in this case, like yeah, there we go, thank you. Like, I get what you mean by the x component and the y component squared. Yeah, exactly. So I was like, yes, you're saying the right thing, but also technically wrong. But I want to acknowledge that it was basically correct. Okay, so if you look at this, the magnitude is the square root of things squared. Now, if you look at the arc length formula, what do you notice about it? It is the magnitude of something, because it is the square root of things, it is the square root of the sum of things squared. So if you look at this stuff right here, you're like, oh shit, this stuff that I'm highlighting in red right here, this is the magnitude of something. And the interesting thing is, the more you look at this, you could figure out actually what it is the magnitude of, because what are the things that I'm going to be squaring? X prime and y prime. And those, quite simply, are r prime. Because r prime is x prime and y prime. So if you take the magnitude of that, the magnitude of r prime is the same thing as the magnitude of x prime t comma y prime t, which is the square root of x prime quantity squared plus y prime quantity squared. So, interesting thing, let's copy this from up above here. I'm gonna lasso it. Okay, so copy, scroll down, paste. So what you notice is that what this is the integral from t naught to t1, and that stuff in red can be replaced with the magnitude of r prime. So, like, one of the interesting reasons for coming up with this vector notation like this is that it simplifies a lot of these integral formulas. So in other words, this is the arc length for a plane curve r of t with components x of t and y of t. Okay. Over the interval t goes from t naught to t1. Okay, and there's like an interesting way to think about this. You can think of the magnitude here as basically being like velocity or speed. And if you think back to like 101A, when you integrate velocity, what do you get? Position, right? And like, you know, arc length is a accumulated position that you've traveled, distance traveled. Okay, now that's a plane curve. Okay, what about if you have a space curve? So what does it mean to be a space curve? A plane curve is some function which goes from r to r2. What's a space curve? Yeah, so a space curve is some function r which is parameterized by a scalar value and goes into R3. So if you're to look at a space curve, your r function is going to have x components, y components, and z components. And do you know what's actually really interesting about this? You can come up with the arc length for a space curve using the same formula as well. Are you looking for something, Hypatia?
Yes.
What are you looking for? My laptop? No! Go get ready to eat and stuff. Sorry, my daughter's like trying to take my laptop so that she can like play Roblox or Minecraft or something before school starts. Alright, so let's say that you want to find the arc length from some t naught value to some t1 value. What you would do is you'd integrate the magnitude of r prime, which for a space curve, what is that going to look like? Well, the magnitude of r prime, so r prime, you do exactly what you do before. You take the derivative of each of the components, so you get x prime, y prime, and z prime. And then you take the magnitude of that. So if you take the magnitude of that, you're going to get the square root of each of those things squared. So you get x prime squared plus y prime quantity squared plus z prime quantity squared dt. Now, what's cool about the vector way of talking about this is that you only have to remember one formula and it depends upon the context. Notice that for both of these things, we have the integral of the magnitude, whether it's for a plane curve or a space curve, and then that becomes some other integral, right? Because then you actually calculate what the magnitude of that thing is, you're going to get the square root of something squared. Okay, so it works the same. It's the same formula no matter what you're working with. Okay, so we're going to do an example of this in a moment. Okay, should I like pause for you to... I'm going to pause a moment for you to write this down. I'm assuming people are writing. Or do we like have it all written down? I can't see anyone, so I don't know. And I don't want to just I don't want to just rush through it. Okay, yeah, cool, I'll pause it. Some people are ready. It's so lonely here with all the black screens or the gray boxes. I just see gray boxes. It's me in the gray boxes every morning, and then like people in the chat. I should just get Mathematica ready while we do this. Okay, I'm gonna scroll down just a little bit. Okay, cool. Okay, so for this example that we're gonna do, let's calculate the arc length for the vector valued function r of t equals, and let's give components. One component is going to be 3t minus 2, the other one is going to be 4t plus 5. Okay, so let's use Wolfram to what's it called? To graph this thing. Oops. I can't click on stuff. There we go. Okay, that's a little better. Okay, so my x of t is going to be equal to 3t minus 2. My y of t is going to be equal to 4t plus 5. Graph that. Okay, so now you can graph it by doing not polar plot, parametric plot. Okay, you give it your x and y coordinates. I'll give it x of t, y of t. I defined those functions already. Okay, and then, oh yeah, let's, we're gonna plot this for, we're gonna find the arc length for t goes between 1 and 5. Okay, so like, let's look at the graph where t goes from 1 to 5. Okay, so you can see that you get a line segment. So looking at this, you can see you have your starting point at approximately, well, if you plug in 1, your x value will be 3 minus 2, which is 1. Your y value will be 4 plus 5, which is 9. So you're going to start at 1 comma 9, and then you're going to end up at that value up there, which is, if you plug in 5, you're going to get 12 comma something, right? So you get a line segment here. Like, let's go through the calculations of like how you would find this. We could figure it out ourselves without using calculus. But let's start off with an example where you know the answer that you're already expecting to get. Okay, so we want to find the arc length from 1 to 5. And basically what you've got here is a line segment that looks like this. Right, so if you plug in t equals 1, what was the point that we got? We got a 1 comma 9. So if this is 1 and that's like 10, 1 comma 9 is like right there. And if you plug in 5, what did you get? It was 12 comma 24. So 20 would be like right there, 30 would be like right there. Say 12 is like right here. 12 comma 24. So you get this line segment right here. This is the distance that we want. Okay, so this formula, what it tells you is that, well, if you want to find this arc length, you're going to integrate from the first t value to the second t value. the magnitude of r prime dt. So the first thing you need to do is calculate r prime. So if you calculate r prime, the derivative of 3t minus 2 is 3. The derivative of 4t plus 5 is 4. Okay, and then you need to calculate the magnitude of r prime, which will be 9 plus 16. Square root of 25 is 5. So this is really nice because you get a constant number. So now your integral becomes the integral from 1 to 5 of 5 dt. This is easy to work with. The antiderivative of this is going to be 5t. So we want f of 5 minus f of 1. Let's move that over to here. Okay, now what are those values? Well, if you plug 5 into 5t, you're going to get 5 times 5. If you plug 1 into that, you're going to get 5 times 1. This is 25 minus 5, which is 20. So according to this, what is the length of that line segment? 20. Well, you can go and verify this by using the distance formula. All right, so you can calculate the distance between 1, 9 and 12, 24. So you would do the square root of 12 minus 1 squared plus 24 minus 9 squared, which is going to be the square root of 11 squared plus 15 squared. Hopefully I calculated these numbers right. Okay, what's 11 squared? 121. And what's 15 squared? 220. Oh, wait. So I must have calculated these numbers wrong when I plugged it in. Okay, wait. Let's go back here. Let's see. If you have t equals 1, let me slowly plug those in. So if you plug in 1, 3 minus 2 is 1. Plug in 1, you get 9. Okay, cool. If you plug in 5, 3 times 5 is 15. 15 minus 2 is 13. Okay, if you plug in 5, 4 times 5 is 20. 20 plus 5 is 25. Oh my god. I can't do basic arithmetic in the morning. Okay, so we go back and change these. I can do all this other stuff, but basic arithmetic is so hard. So you get 13 minus 1 squared plus 25 minus 9 squared. Which is going to be 12 squared plus, what's 25 minus 9? 16. And 12 squared is 144, and then what's 16 squared? 256. If you add those together, you get 400. And what is the square root of 400? 20. Lo and behold, exactly what this formula gave you here. Okay, so what I was doing there was I was showing, like, look, we knew that this was a line segment. We know how to calculate the length of a line segment. I was able to show that this vector formula for arc length gives you the same answer. Okay, and it always works. Okay, so I'm going to pause for a moment. Are there questions on how this works? Like in terms of like using the formula, like going from here to the integral that you actually have to calculate. Pause for a moment. Are we bueno? Pause. No? Not yet? Okay, cool. I will pause, see if there are questions. Hang out for a minute. Bottom left? Oh, yeah, I forgot to change this one right here, yeah. This one right here? Because you do difference of x components. 13 minus 1 is 12. Mm-hmm. Why do you think that, Eric? Oh my god, can you like share it in the chat? Okay. Share it with me. I want to see this. Oh, damn, that sucks. Damn, that's rude of them. I'm sorry about that. Oh, no problem. Okay, I'm gonna scroll back down. Okay, there are things that people want to ask me. Okay, let's talk a little more about these things. Okay, so like, there are a lot of like interesting curves that you can deal with and like a lot of applications of this. If this is the sun right here, then what's the orbit of the Earth around it? What shape does it have? Like, what's the shape of the orbit of the Earth around the sun? Yeah. Oh, okay, 1 second. My daughter needs me to log into something. Can you get me my oh, there, keep. Damn. Sorry, 1 second.
thanks.
Okay, sorry about that. So yeah, the orbit of the Earth around the Sun is an ellipse. So let's say you have like the Earth right here. Okay, so you can, if you wanted to, you could, what's it called? Express the orbit of the Earth around the Sun as a vector valued function. So you could do like r of t equals, and because it's an ellipse, it's going to be something like a cosine t comma b sine t. That basically gives you an ellipse with a major axis length of a and a minor axis length of b. Okay, now also in an ellipse would be like another planet, like Mars, which has like a slightly different orbit. Might look something like this. And you can come up with a vector valued function that would express the orbit of Mars. Let's call it S of t. Would be some other like c cosine t comma d sine t. Now, lately we've heard about there's like that little, what was that probe that made its way to Mars recently and like successfully landed? Yeah, Perseverance, yeah. Interesting thing, like it had to make its way there, right? And what happened was you had to figure out the path that like Perseverance needed to take to get there. So like as Mars is moving, Earth is also moving, right? Like this. And you can actually, one of the one of the uses of this is that you can use vector calculus to figure out like, oh, so if the probe takes off from Earth, it's going to have to follow an ellipse so that it hits Mars, like right over here in a path of its orbit. So you can actually use like the vector valued function for that one, the vector valued function for this one. Why does it say S of t? Because I need a different curve for Mars. For like, I don't want to just say r. Oh, what does it say after S of t? C cosine t comma d sine t. It would just be some other ellipse is my point. And then you would get some other ellipse, or actually it wouldn't be quite be an ellipse. It would be something else. The path of the probe would actually be some sort of like parabola or hyperbola. And it would like follow like that, and you can actually use all that to figure this out. Actually, NASA publishes software that allows you to do these orbital maneuvers. So there's like software that they've made that actually calculates all of this. It's pretty cool. Just so to give you an idea of like when you would want to use this. Now, you would if you're actually sending a rocket, from Earth to Mars, what might you want to calculate on this path? Like, you'd want to know its arc length. So that makes sense? It's like you know that you're going to launch when Earth is right here, and then you want to arrive at Mars right here. You would have to figure out the arc length of the path that the probe would take, right, to figure out like the amount of like fuel you would need and stuff like that. And then basically what they do is they do a calculation like this. It's like a little more complicated because there's more physics involved, but ultimately it comes down to the same thing. You want to figure out the path of the arc length, right, of the curve that the probe took to go from one to the other. So let's look at like an example of one of these curves, or like a curve to talk about this. Okay, so what we're going to look at is, let's start off with something not too hard. Let's use, what should we use? Okay, let's do r of t equals 4 cosine t 5 sine. Actually, let's make it a little different. Let's do 2 cosine t comma 5 sine t. Okay, so let's look at the graph of this. We're going to do that in Mathematica. So I'm going to transfer over to Mathematica. Okay, here we are. So we're going to change our x of t to, what was it that I said? I said 2 cosine t. And let's have our y of t be 5 sine t. And let's have it plot from 0 to 2 pi for the parameter. Let's change that. Okay, so looking at this, what shape do we have here? An ellipse, right? And remember how I was talking about earlier, there's like a cosine t, b sine t. So if you look at the a value in front of cosine, what does that determine? The length of the x-axis, right? Do you see how it intercepts at 2, 0 and negative 2, 0? Now if you look at 5 sine t, do you see how that determines the length of the vertical axis, right? Do you see how the ellipse itself goes from negative 5 at the bottom to positive 5 at top? All right, so is everyone sort of seeing how you can just look at the numbers in front of cosine and sine and get the ellipse? Okay, cool. Okay, so let's copy this picture. And we're going to go back over to here. Oops. Okay, what the hell? There we go. Let's paste it in here. Whoa, way too big. Let's make that smaller. Okay, now we've got our trusty graph. Oops. Okay, I want it a little bigger. There we go. Okay, cool. Okay, so let's put some points on this graph. If you plug in 0 into here, you get 2 cosine 0, 5 sine 0. What's the cosine of 0? You get 1. The sine of 0 is 0, so you get 0. So you get this point right here, 2, 0. Right, that's r of 0. Okay, now let's plug in r of pi over 2. So if you plug in pi over 2, what are you going to get? 2 cosine of pi over 2, 5 sine of pi over 2. What's the cosine of pi over 2? 0. So you get 2 times 0. And what's the sine of pi over 2? 1. So you get 5. So you get this vector right here. R of pi over 2. Okay, now this has some arc length. All right, starting at this point over to here. Let's call that S. The arc length. Oops. The arc length from t equals 0 to pi over 2. Now, does anyone remember the formula for the circumference of an ellipse? Anyone happen to remember? What is the formula for the circumference of an ellipse? Do we remember? That x. I think that's the standard form. What's the form for the circumference of an ellipse? Anyone happen to remember? There's actually a pretty nice formula for it. I'm like looking it up. It involves A and B. Let's see. So the circumference of an ellipse. Oops, why is it not letting me write? There we go. The circumference of an ellipse is equal to 2 pi square root a squared plus b squared over 2, where the a and the b are the numbers in front of here, sine and cosine, with the major and minor axis. Okay, so we can figure out, the reason I want to do this is because I want to figure out how far that is without calculating it with an integral. So the circumference is going to be 2 pi square root 2 squared is 4, 5 squared is 25, over 2, so that's going to be 2 pi over 29 over 2, which if you plug that into the calculator is approximately 2 pi times the square root of 29 over 2 is approximately 23.92. So in other words, approximately, what is the arc length that of my little segment there from r equals 0 to r equals pi over 2? So approximately, what is s equal to? If the circumference is 23.92, approximately what's the arc length from r equals 0 to r pi over? Yeah, exactly. That divided by 4, which is like about 5.98, I think. Right, which is basically 6. You're like, basically 6. Okay. Now, because we're talking about the arc length starting at 0, t equals 0, and ending at t equals pi over 2, what would it be very convenient for this arc length to be equal to? If you started at 0 and ended at pi over 2, what would you like your arc length to be equal to? Like, we know that the arc length is 6. But if you start at t equals 0 and end at t equals pi over 2, what would you like the distance traveled to be? Just to make life easy on you. If I told you, hey, you're starting at t equals 0 and ending at t equals pi over 2, what would you like the distance traveled to be so that you wouldn't have to calculate anything? Well, we already know that the arc length is the circumference divided by 4. But I'm saying, like, in our parameterization, we started off at t equals 0. T equals 0 is right here. And then we ended at t equals pi over 2. Wouldn't it be really nice if the arc length was pi over 2? Does it make sense? If you start off at 0 and end at pi over 2, wouldn't it be really nice if that pi over 2 was how far you actually traveled? Wouldn't it be nice if s was equal to pi over 2. In other words, equal to t1 minus t0. Okay, and there's actually a way to do this. Okay, so this is what we call an arc length parameterization. An arc length parameterization is when the distance between r of A and r of B is always equal to B minus A. Okay, we do not have an arc length parameterization for this ellipse because what was the distance between r of 0 and pi over 2? So what was the distance between r of 0 and r of pi over 2? So remember, yeah, 6, right? Or 5.98, right? Now, if it was an arc length parameterization, what would the distance have been? So if this was an arc length parameterization, what would the distance have been? Yes, exactly. So I'm going to pause to see if this makes sense to everyone about what does it mean to have an arc length parameterization. It means that your vector valued function is set up so that if you plug in t equals A and you plug in t equals B, the distance between r of A and r of B is just going to be equal to B minus A. This just makes it really easy to calculate distances. So I want to pause to see if there are questions about this before I actually do it. Should I wait here longer or can I move away from this part of the screen? Okay, cool. No one says I can't move on, so I'm going to move on. Okay, so the way you find an arc length parameterization is you need to do this. You need to calculate S of t, and it's going to be equal to the definite integral from A to t. So A is that starting point of your curve, t is a variable, and you're going to integrate the magnitude of r prime of u du. Okay, and that's going to give you some formula. So what you're going to do to find your arc length parameterization, you're going to take that formula and you're going to plug it into your r function. And this will be your arc length parameterization. Okay, so we're going to do this as an example. Okay, so let's parameterize. Let's find the arc length parameterization. I can't spell. Okay, that was that thing that we just had. Our R was 2 cosine t, comma 5 sine t. Okay, so if you want to find your arc length parameterization, And let's find the arc length parameterization from oh, actually, it doesn't matter so far. So let's just plug it into the formula. So you calculate your S of t. So you're going to go from A to t of, now you need the derivative of r. So if you go and you calculate r prime, the derivative of 2 cosine is going to be minus 2 sine t. The derivative of 5 sine t is going to be 5 cosine t. Okay, and then now you're going to need the magnitude of r prime u, which is going to be the square root of minus 2 sine u quantity squared plus 5 cosine u quantity squared. Which is going to give you 4 sine squared u plus 5 cosine squared u du. Okay. Making sense so far? Okay, now, we're going to need to find the antiderivative for that. Let me think. How are we going to do this? This is going to be a tricky one. Give me a moment while I think about what the antiderivative for that what we're going to need to do. I think we're going to need to do a double angle formula. Or with a power reduction formula, maybe. Okay, let's think. What are those double angle formulas? Does anyone remember the double angle formulas? Like, what is, like, sine of 2u equal to? Isn't it 25? Oh, yes. That should be a 25, not a 5. Thank you. Actually, I'm just going to cheat a little here. I know what the antiderivative is, but I'm not going to go through the steps to get it. Oh. Let's see. Maybe we can do that. Let's try, see if we can get it. 2 cosine u sine u. Okay, we don't want that one. We need something with a square, though. Is there a double angle formula or half angle formula that has a square? Like a power reduction. What's the power reduction formulas? Let's look those up. Power reduction formula. I'm looking it up right now. Oh, okay, here. We know that sine squared u equals 1 minus cosine 2u over 2. We also know that cosine squared u equals 1 plus cosine 2u. Okay, that might help us. Let's see. So if you wanted to rewrite this, you could do it as... So you could replace this sine squared u with 4 times 1 minus cosine 2u over 2. plus 25 cosine squared u. Okay, so if you were to distribute this, you would get 25 cosine squared u minus 4 over 2 is 2 cosine 2u, and then you would get plus 2. Okay, actually, let's make another replacement here. What can I replace the cosine squared u with? I could put 1 plus cosine 2u over 2. There, I think that would allow us to put them together. Okay, so you're going to get 2 minus 2 cosine 2u plus 25 over 2 plus 25 over 2 cosine 2u. Ooh, I think this might actually work. Okay. So what's 2 plus 25 over 2? It's going to be 75 over 2. And then now we're going to get 25 over 2 minus 2, which is 50 over 2. That's going to be minus 25 over 2 cosine 2u. Ooh, I think we might actually be able to get this one. Wait, no, that's not going to work. Because we can't do a u substitution here. That's not going to do it for us. Okay. I'm not going to go through the details because that's not working. I'm just going to tell you what you get. Okay, if you do this properly, the antiderivative. Okay, why is it not letting me write? There we go. The antiderivative of this ends up being 9u over 2 plus 1/4 sine. Oh, sorry. 9t, you get 9. Okay, wait. So the antiderivative is 9u over 2 plus 1/4 sine of 2u. Okay, which means when you plug it in, you're going to get f of t minus f of a for both of those. So this will give you a formula. You'll get s of t equals 9t over 2 plus 1/4 sine 2t minus 9a over 2 minus 1/4 sine of 2a. Okay, so this formula, what it does is if you were to take that and plug it in to r of t, so you would plug some t into here. So you would take that formula, all of that would go into here, and then all of that would go into r. This would actually plug out a point, or it would spit out a point, which is exactly distance t away from R of A. Okay, so like you can think of the point where that you would get if you were to plug in A, that would like be like right here. Okay, and then the curve, it does something. It moves along the ellipse from here to over here. Now R of S of t, if you were to calculate this arc length right here, you would find that the arc length is exactly to t. It's exactly equal to t. So it's possible to what's called reparameterize the curve so that whatever you plug into that t value, it gives you the point, so that point exactly has that arc length away from your starting point. Okay, and we'll go over another example of this tomorrow. We're like running out of time now. Okay, so keep this in mind. We'll finish this idea tomorrow. We can reparameterize it so that whatever you plug in,